Morning. All right, so welcome back. So we'll just recap what we covered on Tuesday. So we started looking at a little bit of Unity, just a bit of background, and then we had a brief look at the editor and what the various windows are doing, and that's actually pretty much as far as we got because I wanted to talk a little bit about graphics before we got any further into that. So then we started talking about programming graphics, and we talked about 3D graphics and processing, how there are multiple different renderers we can use, and if we want to do 3D stuff, we use the P3D renderer. We looked at this example, and then we broke that down into what each individual line did. Hopefully you guys were comfortable enough with looking at that, sort of what was going on. And then we got into primitives. So we looked at a handful of primitives that are available in processing, and I sort of talked about how some of these are standard across all graphics rendering API, and some are kind of unique to processing. So just to recap, there was points and lines. So points were, it's very hard to see here, but points are basically an individual pixel. So they're a point in 3D space, which is infinitely small. And then we have lines, which are made of 2 points, so one at either end, and these are, have a length, but effectively have no width or anything like that. So those are both supported by pretty much everything. Then we looked at some two-dimensional objects, so we looked at triangles, and in particular we looked at, so these are triangles here. This is a little bit confusing the way this is laid out, sorry. This is triangles, then we have a triangle strip, where, so for triangles, we take every 3 points and make a triangle out of them. For triangle strips, we take the first 3 points and create a triangle, and then when we get a new point, we take the last 2 points in our new point. So we have point 0, or 1, 2, and 3 to draw that triangle, and when we see point 4 here, we would take 2, 3, and 4 to draw a triangle, and then when we saw point 5, we'd take 3, 4, and 5 to make a triangle, and so on and so forth. And then we talked about triangle fans, where we take, again, the first 3 points, 0, 1, 2, and 3, to draw a triangle. And then for each additional point we get, we take the very first point and the most recent point. So we'd have 1, 2, 3, draw a triangle. And then if we added 4, we'd have 1, 3, 4, and draw a triangle. And then if we had 5, we'd have 1, 4, 5, and draw a triangle, and so on. And all of these are available in any rendering API as well, and in fact we looked at, in our example in Unity, we looked at this killer whale that we got off the Unity store, and we saw when we look at it that whale is made up of triangles. So the entire mesh for that whale, everything is made of triangles, as will be the monsters we downloaded. They will all be made of triangles. So there's the bat, there's the ghost, the rabbit, and so on. So the only shape you'll see in these are triangles. However, I did mention that some graphics API, well actually most graphics APIs, if not all of them, will support quads as well. But we can easily create a triangle from a quad simply by breaking it diagonally. So if we have a quad here made of 4 points, we could just say points 1, 2, and 4 are a triangle, and 2, 3, and 4 are a triangle, and convert quads into triangles anyway. And there are two forms of quads. There's quads, quads is normal, where we take every 4 points, so 1, 2, 3, 4, 5, 6, 7, 8, and make a quad out of each of them. And then we have a quad strip, where we do the same thing as our triangle strip. We take 1, 2, 3, 4, and then for every additional set of every 2 new points, we create a quad out of the 2 new points in the 2 previous. So if this is, let's do it this way, 1, 2, 3, 4, and then we add 5 and 6, we would go 1, 2, 3, 4, 3, 4, 5, 6, and then 7, 8, 4, 5, no, whatever we're up to. 5, 6, 7, 8, sorry, 5, 6, 7, 8. And those are available. So basically all of these ones up here are available in every graphics engine. Most commonly, people are concerned with triangles because, as we saw in the Unity models, you can make anything out of triangles. Processing also provides a couple of arbitrary shapes. So if we go back to our begin shape example, So we can see here, we normally say begin shape and then describe the shape. So points, lines, triangles, triangle strip, triangle fan, quads, quad strip. But if we pass in no arguments to the begin shape method, we can just start putting points in and it will create any arbitrary shape based on those points. And if we have in-shape close or we have in-shape without close, actually this is a better example here, we can see if we have 1, 2, 3, 4 with no close, it will just draw those 4 lines. If we have close at the end, it'll go 1, 2, 3, 4, and then it'll take the 4th point and the 1st point, so the last point and the 1st point, and connect them with a line as well, so it'll close off our shape for us. So those last 2 examples down here are processing specific. You don't see this in Unity or many other languages. We normally would have to basically, if we wanted to draw these shapes, we'd have to do that manually. So if we wanted to do this one, we'd have to make it out of lines. So we'd go draw a line from 0 to 1, 1 to 2, and 2 to 3. For this one here, we'd have to break this into quads or into triangles. So you can imagine there could be a quad there and a quad there, or a triangle there, or rather a triangle there, a triangle, one triangle there, one triangle there, one triangle there, and one triangle there. Cool, so let's have a look at another example. I didn't open processing, that was silly. So this is another example for processing. This time we're drawing a slightly more complicated shape out of these primitives. So if you remember, we looked at some examples of compound shapes. Where were they? What was it called? Box. Yeah, well, they call them 3D primitives, but really they're not. Well, I guess, yeah, terminology, but I call them compound shapes because effectively they're made up of primitives. But they've called them 3D primitives, so they have box and sphere. So you'll notice those are the only 2 that are there. There is one for a box, there is one for a sphere. But if we copy and paste this code in, you can see that we've effectively drawn a pyramid. And if we look at the code for this, it shouldn't be too hard to figure out. We'll have a crack at doing it on the board like we did on Tuesday. So if we say we have, so this will be the x coordinate from -100, 0, 100. This will be the z coordinate this way from 100, 0, -100. And then we have the y coordinate up here from -100, 0 to 100. Hopefully that's, probably should check what the bounds of this thing is, the shape are. So it looks like that just goes from 0 to -100. So let's just follow their example, 0 to -100. Okay, so I'm going to do my best to draw this shape in 3D. You have to bear with me because I'm not an artist by any stretch of the imagination. Okay, so that's roughly our grid in that space. Let's actually connect those up so we can see. All right, so let's go through. So we've got begin shapes triangles, so we're going to draw some triangles. The first one is going to be at -100. Oh God. There we go. -100. Actually, let's make that 100, not -100, so everything's on the same. Okay, so -100 by -100 to 100 by 100 and -100 up because it's just being difficult. Right, so anyway, so we're going to start at -100. No, I apologize. I'm trying to make this consistent so that it's going to appear the same in my drawing as it will on the screen. Okay, so 0 is at the top, -100 is at the bottom, and then we've got -100 by -100. Okay, so our first point is at negative 100 in the x, by negative 100 in the z, by negative 100 in the y. So it's going to be there. Our second point is at 100 in the x, by negative 100, negative 100, so it's going to be there. And our third one is at 0 in the x, by 0 in the y, by 100 in the z. God, this is going to be a mess. Okay, so that's our first triangle. So our second one starts at 100, negative 100, negative 100. So that point there, then it goes to 100 by 100. Oh God, okay, I'm going to give up on this because I've already messed up that I didn't check my bounds. So that should have gone, that y value should go to negative 100. Sorry, all from negative 100 to 100. And this is going to prove to be very difficult to draw by hand in 3D. So I'm actually not going to bother about it. You're just going to have to take my word. But if we go through, basically what we'd find is that we have 3 sets of triangles here. 1, 2, sorry, 4, 3, 4. And if we actually did a good job at drawing those out, maybe use some graph paper rather than trying to draw it freehand on the board, we would see there is a triangle here. There is a triangle here, a triangle here, and a triangle here. And the fact that it looks like it's got a square for a base is actually kind of irrelevant. What we actually can do is we can actually go, let's put begin shape and end shape at the end of each of these just to make it a bit easier on ourselves. So now we can more clearly see there's a triangle with 3 vertices, triangle with 3 vertices, triangle with 3 vertices, and triangle with 3 vertices. And what I can do is I can change some of these to fill. I'll change them. Let's do 1 and 2. So this first triangle here is that one at the back. The second one is, need to put no fills on all of these. The second one is the one on the right hand side. Third one is the one at the front, and hopefully no surprises. The final one is the one on our left-hand side of the triangle. So you can see there are the 4 triangles, 1, 2, 3, 4, which are being drawn, and you'll notice that there's no shape for the quad at the bottom, that's just there. And likewise, as we saw in the other examples, we've got some translate and rotates to basically put it at a more interesting angle rather than just face forward. So my apologies that I failed miserably at trying to draw that on the screen, but hopefully by going through something like that, you know, filling in each of the triangles one at a time, you can actually see where the 4 distinct triangles are sitting. Fortunately, there are some better examples than the ones that I try and blunder through. So I think I talked about this in one of our earlier lectures. When you see an example or when you see something which looks like this, topic/geometry/RGB Cube, what that is that is a processing example. So if we go into examples, and hopefully these are still in the same place, topics, geometry, RGB Cube, and we open this one up, you'll see now we have this lovely pretty colored RGB cube, or cube floating around. So there's one thing we haven't talked about yet. Let's actually look at that just now. So when we are drawing our pyramid like this, we notice we use fill and no fill, and that will allow us to set the color of an entire side. But perhaps that's not, perhaps we want to do something more than that. We want to set the color per corner. And there's actually a function called fill, which allows us to apply a corner to a specific vertex. So what I can do, let me just copy a few bits of code out of here. So hopefully if this works. So now you can see we've got this one side of the triangle, rather than just being the flat grey colour that we had before by setting fill to 192. Instead we've got this sort of colour which goes from cyan to purple to red. So what's happened here is for each of these vertices, so we have 3 vertices which define the 3 corners of the triangle. We can use fill to specify the colour that that vertex should have. And the nice thing about doing that is that the graphics API will actually blend between the colours nice and smoothly. So we can see there's a nice blend from the blue to the purple and the blue to the red and the red and the purple and every other possible combination of colours in between that. So we've got 3 colours in here. This first one here is our cyan colour, so fill 0, 255, 255. If we look at the colour selector and punch that colour in, we'll see that's that colour there, which matches with the colour in that bottom corner. And so this corner down here, this negative 100 by 100 by negative 100, would be that corner there. Our second one, which is 255, 0, 255, is that gives us that purple corner. So if this one here, the cyan, is that bottom left, bottom right, this fill is the bottom left, or this vertex here is the bottom left, and finally fill 255, so red 255, green 0, blue 0 is red, and that will be our point at the peak of the peak of the pyramid here. So we can actually fill in each colour individually. We don't have to use one overall colour, and that's exactly what's happening in this RGB Cube demo. The only thing to be aware of in this and how it differs from what we've just done here is that they use this color mode RGB1, which basically says instead of RGB values going between 0 and 255, they should go between 0 and 1. So when we run this, if we look at these fill values, if we can find them, you'll see they're all 111, 110, 100, rather than 255. If we didn't have that line of code there, it would be expecting the color mode or the color values to be between 0 and 255, and so our cube doesn't actually appear because all the values are either 000 or 111, which is black and almost black. So this is a slightly more complicated example than we have looked at so far, but it's actually not that bad. So we set up our background, our renderer. We turn off strokes so we don't get the lines dividing or the outlines for each side, and we set our color mode to 1, so it goes between 0 and 1 rather than 0 to 255. Then in our draw method, we draw a grey background. We call push matrix, which we talked about a little bit, how that basically saves a position. We'll be talking about that more today. And then we move the origin of the world, again we'll talk about that more today, into the center of the screen. So width divided by 2, height divided by 2, and 30 into the depth. We calculate the x magnitude and y magnitude, which is the mouse x position between 0 and 1 and mouse y between 0 and 1, and use that to do some rotations. So as I rotate around, as I move the mouse from left to right, it will rotate it around the y-axis of the cube. So if you remember, if we have x is moving left to right, y is moving up to down, and z is moving in and out of the screen, then if we have an object, moving it in x-axis, we'll move it that way. Rotating it in the x-axis is like we've put a skewer through the device in that direction. So if we're moving in x that direction, we're rotating in x that direction. If we're moving in y that direction, we're rotating in y that direction. And if we're moving in z that direction, we're rotating in z that direction. So moving the Moving the mouse from left to right will rotate in the y-axis, as we can see, rotate y, x mag, and moving the mouse in the y-axis, so up and down, will rotate around the cube's x-axis. Then we use the scale function, so that's just going to scale up everything by 90. So when we see the value 1 or -1, it's effectively 90 or -90. Just because the reason I've done the scale to 90 and the color mode to 1 is that way when we draw our cube, it's nice and easy. Everything's just 1s and -1s. And I can probably draw this one on the board actually, because this is a little bit simpler. I've spoken too soon. Go down there. And there we go. Okay. So let's say that's -1, -1, -1. Wow. So this will be the x-axis, this will be the z-axis, and this will be a very crooked y-axis. So this is -1 in x, 0 in x, 1 in x. This is -1 in z, 0 in z, 1 in z. And where can I put this? This is -1 in y, 0 in y, and 1 in y. I apologize if that's kind of hard to see. So our first one is going to go from -1 by 1 by 1. So it's going to be that point there. Then we're going to go 1, 1, 1, which will be that point. What on earth is going on here? There. Then 1 by -1 by 1, which will be that point there. And then -1 by -1 by 1, which will be that point there. And that will be the back side of our cube. If we go in through each of these, we'd see there'd be this one here, then there'll be another one which will go there. There'll be another one which goes there, and then there'll be one which goes, apparently I cannot draw a straight line to save my life, and then there will be one on the top and one on the bottom as well. So in total we would expect to see 6 cubes, or 6 quads here, because these are being rendered as quads. There's 1, 2, 3, 4, 5, 6, and that's all we get. And likewise, we have these fills for each color. So if we look at this first one, so this is, if we open the color selector, 0, 255, 255. So this first corner has a cyan color to it. So where's the one with cyan? So it's that corner that's facing the screen is this first corner. Then 111 is white, so it has to be one with cyan and white. So it could either be this side here, because we can see cyan in the top corner and white in that top corner, or it could be this side here. And then we have the third one down is purple. So it's got to be that one there. So this first side that we draw on the back of the screen is this side here, and we have this -111 will be with the cyan, will be that corner. 111 is white, will be that corner. 101, which is purple, will be that corner, and 001 is blue, which is that corner. And we can do that for each side of this thing. So we find the next one. This is white. What's that? Yellow, I think. Yeah, white, yellow, red, purple. So that will be white, yellow, red, purple. So white, yellow, red, purple. And we could do this for each side and identify what each side is. So that was side 1, that was side 2. It's a pretty safe bet this will be side 3. So it will have a green. It will have a, oh wait, no, that can't be. It must be that one. Oh, this is black on this side. Must be that one. So that'll be green, cyan, blue, black. and that's got green, yellow, white and cyan. So green, yellow, white, cyan. And our last one has black, blue, purple, red. So black, blue, purple, and red. If you don't trust me, you can go through and if you comment out, so for example, if we commented out that set of quads there, remembering that was black, blue, purple, red, we'll now see that we have a box with a hole in it and there is no side which has black, blue, purple, or red anymore. That's, yeah. So yeah, that is a very, it seems like quite a convoluted way of drawing 3D graphics, and it kind of is. But hopefully, you know, you guys can look at that and see, well, actually, if we break it down piece by piece, as we've just done there, set up the screen, turn off outlines, set the color mode so that it's between 0 and 1, set the background to gray, move it to the middle of the screen. This stuff here I wouldn't worry too much about. That's just basically rotating it based on the mouse's X and Y position. Scale it up by 90 and then draw a bunch of quads. And each quad, well, quad's made of 4 vertices because a quad has 4 corners, and each corner has a color and a position. And we just do that 1, 2, 3, 4, 5, 6 times, call in shape, and we're done. And then we have this nice little demo here with this quad that moves around and it's nicely colored and everything. Is everyone comfortable that if I gave you an example like that and asked you to do something, you know, change the colors on the quad, change the shape of the quad, you know, I wouldn't expect you guys to be able to necessarily write this all from scratch, but if you had an existing copy, hopefully you'd be able to, if I said make each side a solid different color, so make one side all red, make one side all green, do you guys feel comfortable that you could probably achieve that? Cool. Okay, so again, it seems like it's really hard, but if you actually step through it, it's actually not that bad. So there's another example here, topics, geometry, vertices, which we actually talked about a little, this sort of example a little bit on Tuesday. So here we see what appears to be a sort of cone. So it's got a cone-shaped shape to it, and then it's got a circle cap. We can't actually rotate it around to see the back, but I'm pretty sure there's a circle on the back as well. So this has got a lot more going on to it than the last one did, because it tries to be more, it tries to do more. So you see we have this draw cylinder method. So in our draw method, we set up the background, we turn on some lights, move some stuff around. And there's 3 different examples that they have here of draw cylinder methods. If we run through, we've seen the first one. The second one is literally just a cylinder, but it's a bit smoother. And then the third one from memory is a pyramid. So there we go, it's a pyramid with 4 sides in it. So if we look at this draw cylinder method, it's kind of complicated, but it's not too bad. It takes in a few arguments. The top one is the radius of the top, so how wide the top should be. So in the example of that cone, oh sorry, actually let's talk about the first 2. So we have top radius and bottom radius. So one defines, if you think about a cylinder, how large the top is and how large the bottom is. So in that first example of the cone we had, the top is 10 and the bottom is 180. So it has a small top and a large bottom, and that's why we have that cone shape to it. For the cylinder, the top and the bottom are the same size, so they're the same. And for the pyramid, the top was 0, so effectively it comes to a point, and the bottom is quite large. Then the third argument we have is tall, so how high it is. So yeah, the cylinder and the pyramid are taller than, the cone and the pyramid are taller than the cylinder was, and then sides defines the number of sides we have. So the first one had 16 sides, which is why it looked quite angular. The cylinder had 64 sides, so that was why it looked quite smooth. And then the bottom one, the pyramid, has 4 sides, which is why it's a pyramid. If we look at the draw cylinder method, it's a little bit more complicated because it's using sine and cosine to calculate the shapes around a circle, keeping in mind, now I'm probably going to bumble through this as well, but Do your best. Do you guys all know SOHCAHTOA? Okay, cool. So, takes me back to high school geometry. So SOHCAHTOA is a nice, easy way of remembering the relationship between sine, cosine, and tan with a triangle. So if we have a triangle, right-angled triangle, which looks like this, and we have some angle here we'll call theta. So if this is the angle we're looking for, this is known as the adjacent side, so the side which is next to it. This is known as the opposite side because it's the side which is opposite to the angle, and of course in a triangle that's a hypotenuse. So we have SOHCAHTOA, and you notice we have OH, AH, and OA, so that's OH, AH, and OA, and the S, C, and T stand for sine, cosine, and tan. And basically the way to think of each of these is if we put them in a nice little pyramid like that, we have, wait, hold on. So we take, for each of these, take the first letter and put it on the bottom left, then the second letter on the top, and the third letter like that. And so if we want to figure out any of these things, we know that if we want to do sine, it'll be sine theta equals opposite over hypotenuse, cosine theta equals adjacent over hypotenuse, and tan theta equals opposite over adjacent. So that's basically SOHCAHTOA. If we put each of the letters in the shape, then if we want to calculate anything, so sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, tan theta is equal to opposite over adjacent. Or the idea behind putting it in the pyramid like this is whatever you're looking to find, you cover that one and write the other thing. So if we were looking, for example, to find the length of the adjacent angle, we would say it is the size of the opposite over tan theta. So cover that, and O over T. Or if we wanted to know O, we'd cover that, and it would be tan theta times adjacent. Okay, so this may seem all a bit arbitrary, and why are we talking about this? So if we want to draw a circle, what we can do is we can take the point in the center of that circle, and we can just use sine and cosine to work our way around that circle, because we're just calculating 360 angles, and use that to figure out a point on each of these. So let's say I want to do my first one at 45 degrees. So I want to calculate ideally that point there. So it's probably closer to 30 degrees actually. So we know two things. We know the angle at each point, and we know the radius of the circle. So the radius will be h. So we know the angle is 30, so theta equals 30. We know h, let's say this is a circle of radius 1. So we know theta, we know h, and we're looking to find this, the value of x will be equal to O, and the value of y of this point will be the adjacent, because it's the adjacent next to it. So we have these two pieces of information, so all we have to do is say, okay, I know the hypotenuse and I know theta, I want to calculate O. Which one has theta and the hypotenuse and calculates O? Sine does. So sine opposite hypotenuse, and if I want to find the opposite, I just have to say sine theta the opposite is sine theta times the hypotenuse. And likewise, if we do this for the adjacent hypotenuse, we have this one here. So adjacent equals cosine theta times the hypotenuse. And if we do that, we will calculate relative to the center of the circle how far up we need to go as the adjacent, how far to the right we need to go as the opposite, and that will give us, knowing the center point of the circle, the hypotenuse or the radius of the circle, it'll tell us where that point lies on the outside of that. So if we wanted to draw a circle, all we have to do is start from the center and then just gradually increase our theta numbers. So we start at 0, then 1, 2, 3, 4, 5, 6, and do these calculations numerous times, and that will give us all the points around the outside of that circle. And that's literally exactly what this function is doing. So there's 2 vertices in here that are 2 vertexes because it's calculating the top and the bottom at the same time. But if we just look at this top one, so this is just doing the top, so we're looking at the top radius times cosine angle times top radius, so we said radius is h, and 0 because it's at the top of the thing, and then top radius times the sine of the angle. So top radius times the sine of the angle will give us O and A, and so that is basically, this thing will go for around the number of sides. Angle we just increase every time we go around, and so that this for loop here is basically going around. If we say let's draw one with 16 sides, it's going to go around 16 equally spaced angles. I don't know what count I'm up to now, but you can imagine, and then it will basically draw a circle which looks like that. So we'll do that for the top and the bottom, and in fact what this one's doing is it's a quad strip, which we know is where we go and draw a bunch of quads like this. So what this is actually doing here, because each vertex goes from the top to the bottom, it's actually drawing the side of our, the side of our cylinder or the side of our pyramid or cone or whatever. So that first part we looked at is actually drawing this side. So it's going from the top to the bottom, and then bottom, top, bottom, top, top, bottom, bottom, top, bottom, top, and so on and so forth. So it's going basically across here, and it's drawing each of those side pieces. And then if we scroll down a little bit, we'll see one which is doing the top. So it does the top radius, and this time it's using a triangle fan, and it's doing exactly the same process. But if you remember a triangle fan, we have the center point, and then we draw a triangle, and then we draw a triangle, and so on and so forth. So this uses exactly the same equation, top radius times cosine angle, top radius times sine angle. But the first thing it does is it puts one point in the middle, and then it just calculates each of those and draws the top. And then the next one down will draw the bottom. So it does the same thing, puts the point in the center, so tall is just the height of it, and then goes around the number of sides and puts in bottom radius times cosine angle, bottom radius times sine angle. And that's it. So again, it's more complicated than you guys need to know, but hopefully if you sat down for a while and did the maths yourself, you'd be able to actually do this. So, the math is not super complicated, it's just one of these things that you need to think about. But hopefully at least you can sort of see now we're actually starting to generate models and interesting shapes and stuff out of just triangles and squares at this point in time. So again, hopefully, you guys might be able to do something like do a fill or set fill on each of these, so you can actually have a nice spectrum of colors around the top and the bottom and around the side. If anyone wants to have a crack at that and send it through, we can show it in class and you can claim your credit, which is worth nothing. But it's if this sort of stuff is interesting to you, and this is I do actually find this stuff quite interesting. I'm probably one of the few people who does. But feel free to have a crack and see if you can do something like have a color around the outside or a color on the top or the bottom or whatever. But otherwise, hopefully, at least with something like that and breaking it down, you can follow along what's actually happening internally in the program there. Because that's all I want to say about custom doing geometry. So the good thing about Unity and stuff is that we actually don't have to do that. So we can just import, as we saw the other day, if I click on game object and then 3D object, you can see we get a bunch of these compound objects that we can throw in quite easily. So we've got things like cubes, we've got spheres, we've got capsules, which is like two spheres connected by a cylinder. We've got cylinders, and we've got planes, which is just a flat surface. And we have quads, which is also just a flat surface, but this one's only made of 4 vertices, so the 4 corners, whereas this one's actually made up of a bunch of different, or more than 4 vertices if I rotate this around. So, but you can see, so for example, if we look at our quad here, and I can actually, so we didn't really go into too much detail about this on Tuesday, but we talked about how we have game objects and they have components attached. So I mentioned the mesh renderer, and that's responsible for basically drawing it. But there's also this mesh filter, and this mesh filter will contain the mesh that is getting drawn. So in this case, we can see this quad mesh filter has a mesh called quad, and if I double click on that, I can actually see what this quad looks like. And we can see this is made up of 4 vertices and 2 triangles. So 4 vertices, 1, 2, 3, 4, and we can see the 2 triangles with a line down the middle of them. Likewise, we can do the same for our cube. So this one's made of 24 vertices, 1, 2, 3, 4, 6 times 4 effectively. It's made up of 12 triangles, so 2 for each side. Our sphere, we can see, is made up of lots of triangles, 515 vertices and 768 triangles. So we can see that's our sphere. Capsule, again, is made up of you can see a triangle strip basically in the middle, and then there's sort of 2 sphere shapes. Our cylinder looks exactly like the ones we just made in processing, so you can see there's a triangle fan on the top, and there is a triangle strip on the side. So hopefully you guys using this could write or could understand what's happening there. And then I mentioned we have a quad, which looks like this, so it's 2 triangles, and we have a plane, and the difference between a quad and a plane is made up of a whole bunch of triangles in a grid. And the reason for that is for various lighting effects and stuff like that. So a plane we can put shadows and stuff on, whereas a quad we can't as easily anyway. Okay, so that's graphics primitives, how just basically wanting to get you guys to understand that everything is made up of, in the same way that all matter in the real world is made up of atoms, everything in 3D graphics is made up of primitives, which are usually triangles, effectively. It's not something that, you know, certainly in my career, I can probably count on my hands the number of times I've had to work at the primitive level. But it's definitely useful to know that, because when things start going wrong, if they go wrong at the primitive level and you don't know anything about it, like you've got, we'll talk about later, but things like surface normals pointing the wrong direction, then everything looks really weird and you have no idea why and no idea how to fix it. If you go into 3D modeling, so go and have a chat with Shun, he'll show you in his 3D editing programs, he often does work at the vertex level, so he's manipulating quads and triangles directly, so that he can get the biggest bang for your buck out of. The more triangles or quads you have to draw, the more processor intensive it is, the slower it runs. So ideally you have this trade-off between making it look really nice by adding tons and tons of triangles and making it run really well. And that's where computer graphics goes from being science and engineering to an art form, being able to create a 3D model out of the minimum number of triangles and still have it look good. And that's actually something as part of whenever we work with a client, that's one of Shun's first jobs often, if we have a wide range, or if they send us some content. For example, we just finished, we did a project with Paramount around the new Bumblebee movie, like the Transformers Bumblebee movie, and they sent us some models of Bumblebee which were made for the movies and were, you know, hundreds of millions of triangles effectively, and we needed that to run on an iPhone. So Shun spent about 2 weeks basically deleting as many triangles as he could without making the model look like really boxy and square, which sounds painful, and I think I would find it very painful, but he's really good at doing it. And you know, the end results speak for themselves. We have these models of Bumblebee now, which look, you know, unless you're really looking for it, don't look that much worse than the movie quality models they sent through. But instead of being 100 million triangles, they're like 100,000 triangles. So you know, there are automatic processes which will remove them. They basically say these two triangles which sit side by side, kind of, you know, could I do one triangle which would encompass them both? But according to Shun anyway, they're not as good as you would hope. So and they're very unintelligent. They just basically say, oh, well, let's just try and flatten everything, or let's, you know, you basically say, I want to remove this much, and they'll remove that much indiscriminately. Whereas obviously, if it's a 3D model, there are certain parts which may be more or less important. So for Bumblebee, you know, we can maybe remove some of the parts on his chest plates or whatever. For those of you who don't know what I'm talking about, has anyone seen the Bumblebee movie? We got some, yes, we got some no's. So this is no, that's the wrong one. This is Bumblebee here from the new movie. And so there are parts, you know, if you flatten out some of the parts in the body panels, so he transforms from a car into a robot, it's probably going to be less noticeable than perhaps if you remove some polygons from his head, because then his head starts looking quite square and boxy. And there's not, as far as I'm aware, there's not really any tools where you can sort of do that. Leave this part alone, but remove some polygons from here. So Shun will often do a first pass with automatic stuff at a low threshold, which might take it from 100 million polygons down, or 100 million triangles down to 10 million or 1 million. And then to get it from 1 million to 100,000, he does it manually from there. And it takes a very long time, but that's life. Okay, cool. Any questions about primitives? No? Everyone's still with me? You all still look awake, but I can't see your screen, so possibly you're all just on Facebook or whatever. Okay, so talking about polygons, we're going to leave that behind now, and we'll bring it back up a little bit later on, but if you didn't understand that, or it's incredibly boring to you, that's fine, because we're going to move on. We're going to move on to transformations instead. So transformations are much more useful, and you'll probably find yourself working with these most of the time when we're talking about 3D graphics. So again, we have some examples in processing, basics, transform, translate. So there are three main types of transformation in our nice Euclidean Euclidean world. And they are translation, which is moving. There is scaling, which is changing the size of stuff, and there is rotation. So we've got a few examples here. This first one, actually this isn't really the best example of translation. Yeah. But yeah, so translation is basically shifting something in three-dimensional space. So we've looked at this in Unity already. So I can click on one of these things, and if I go to the Move tool, we can see that let's get rid of some of these other things. So if I go to my cube now, we can see it has three arrows on it. One is pointing in the X direction, and that's in Unity shown as red. One is pointing in the Y direction, which in Unity is shown as green. And one is pointing in the blue direction, which in Unity, in the Z direction, which in Unity is shown as blue. And I can click on any of these arrows and use it to slide my box along one of these axes. So if I click on the red one, which is X, and move it back and forward, we can see in our transform position over here, this value is going to get smaller as I move it in the direction opposite of the arrow, and it's going to get larger as I move it in the direction of the arrow. And same for Y. Now we can see the Y, as I move it up, will get larger, and as I move it down, will get smaller. And Z, as I move it in the direction of the arrow, will get larger, and in the opposite direction of the arrow is smaller. And that is translation. So it's basically moving things around in space. So in processing, I do have this example, but just thinking about it, it's not really that great. Kind of shows other things better. But basically we have two boxes here. So if you remember back when we were doing our object-oriented programming, we made that car demo. So this is kind of like that. In the car demo, we were drawing the Rex with the position. What this one's actually doing though is it's always drawing the Rex at the same position. So it's always by dimension, which is 80. So the value of dimension never changes. So it's always drawing it at negative 40 by negative 40 by 40 by 80 by 80. So it's drawing a rectangle which starts at negative 40 by negative 40 and is 80 pixels wide and 80 pixels high. And we'll notice these two rectangles are the same. So in the car example, we had the car X and car Y positions to dictate where they are. Here they're actually always drawn in the same position, but we're using these translate functions to move them across. So just to prove that to you, if we comment out these translate functions and run it, you'll see that they're not going anywhere. And in fact, if I comment out the black one, we'll see the white one sitting underneath it. So they are just being drawn in the same place on top of each other. And it's these translate functions which are moving them. So the first one, we translate by x, and we translate by height divided by 2 by dimension, height divided by 2 minus dimension divided by 2. So basically, this part's just putting it roughly in the middle of the screen. And the x value is, or x is a value which just increases by 0.8 per draw call. So the value of x, if we just print that out, will just gradually increase as it goes. So that is moving. Let's actually just comment out the black one for a second and just focus on the white box. That is moving the white box by 0.8 units every frame. So it's gradually going along. There is also this piece of code here which basically says if the value of x is greater than the width of the screen, set it to be on the left. So again, in our car demo, we had this thing, if x is greater than width, set x to 0 so that it constantly, once it goes past the end of the screen, it puts it back to the start of the screen again. So we can see this is, again, doing the same thing. It's going around and around, except they, instead of doing 0, they do negative dim, so it's kind of off the back of the screen, and plus dim. So they're just waiting until, you know, if we followed this along, if I go roughly the same speed, it will go roughly 1 width, and then it will pop back here, and then it'll come back in. So it's just off the screen, whereas our one reached the end and then disappeared and popped back. So basically each time we draw this white car, or this white box rather, we move first to the position of x, and then we move down, move the position halfway down the screen rather, and then we draw that white one. Okay, so.
Adrian, where are we controlling the speed here?
So the speed is in this x equals x plus 8. So if I wanted to make it move faster, I could change it to x equals x plus 2, and now we'll see that's moving a lot faster than it was. So at each frame, the value of x is increasing, and we move by each frame. Okay, so now this is going to be where things get a little bit tricky. So I mentioned before on Tuesday, Unity uses a scene graph to represent the position of objects in space. And if an object is a child of another object, if we move the parent object, the child will move at the same time. Does everyone remember that? Hopefully. So when we're doing 3D graphics normally, it actually works a little bit differently. And I did talk about this very briefly. So we have what's known as the coordinate system, or the world coordinate system. And basically you can think of that, I use the example of like a mouse pointer in 3D. So initially, our mouse pointer starts at 0, 0, 0, and it will start with its, you know, it's X pointing in one direction, it's Y pointing in the other direction. I really need to 3D print out one of these for an example. But if we think of my Unicard here as world origin, it's going to start in that position. And so what's happening if we think about this example here is the first thing we do is we translate it by X and by this height divided by 2. So let's say we're going to translate by x and by the height. So we're going to move it, let's say x is this way and y is this way. We move it by, say, 10 units in x, and then we move it down by 5 units. And then what we do is we draw our rectangle. And the rectangle, or anything that we draw or create, is always going to appear on our mouse pointer, our coordinate system. So that's going to get put basically where that coordinate system is there. So if we have a look at our second thing here, you see we have this translate x dimension. Now you might think, well, this is translating by x in the horizontal position, and this is translating by x in the horizontal position. So those two cars should actually always be side by side in the x dimension. But we'll notice if we run it, the black car is actually moving twice as fast as the white car. And the reason for that is because of this idea of like this 3D cursor or mouse pointer, which is the coordinate system, all of these things accumulate. So what's actually happening is if this is car 1 and this is car 2, we start at 0, 0, and we move, let's say the value of x is 10, and let's just say, change this to 10 and this to 5 or something. Let's do 100 by 50 then, just to make it a bit easier on ourselves. Okay, so the value of x is gradually increasing, but we're always printing this. Do the first one, move it by x and move it down by 100, and move it by x and move it down 50. So if anything, we'd expect them to be in the same position, and the second one, which is black, the first one's white, to actually be slightly higher. But what's happening is we move this, our mouse pointer. Let's say x at this point in time is 10, so we move it 10 units across, and then we move it 100 units down, and we draw our white car. But when we do this next translate function, we're not actually moving this back to 0, 0, we're moving it from where it is now. So what we're doing is we're now moving it, we said x is 10, we're moving it another 10, and now we're moving it down by 50. And so this is my white one, and this is my black one. Now if you think about this, when we go around to draw it the second time, so we're back, every time we call draw, we start back at 0, but only when we get back to the start of draw do we set that position back to 0. As long as we're still in the draw function, it's just going to keep increasing. So if this was x is 10, let's imagine now x is 20. So we're going to move 20 units out and 100 units down. And so this one's going to be here. But now we're going to move another 20 units out and another 10 down. And so the black one's going to be here. So each time we're moving 20, or x for the first one, and then another x for the second one. So if it's 1, the difference is going to be 1, and 1 is 2. If it's 2, it's going to be 2 and 2. 2 and 2, so the difference is going to be 2, then 3, then 4. So at each point in time, if this one is moving 1 unit, this one's moving 2 units. So what happens is that each time it's getting moved twice as fast as the other one. And that's exactly what we're seeing here. So this black box is moving twice the speed of the white one, because each time this moves 1 unit, the x moves 1 unit relative to it. So it's basically moving at twice the speed. So what we can do, we talked about this a little bit, again, very briefly on Tuesday, is we can use GL push matrix and pop matrix. And what that does is that saves and loads the position. So if we do push matrix before that first translate, so it's sitting here, we say push matrix, and we're basically saying save the position of that. And then we move it out, draw our box. We'll do the white one. And then when we say pop matrix, we're basically saying load that last position. So that one will go back to there. And then we do our second movement by x, by whatever, and that will end up there. So if I have push matrix and pop matrix here, we'll notice that now, because these are both moving at a speed of x, that they're both moving at the same speed, because we move out, draw the white one, and then go back to the start, and then move out and draw the x one. So that's probably the most confusing thing to remember and to sort of understand about 3D graphics and 3D transformations, is that they are all accumulative when we're dealing with regular 3D graphics. In Unity, because everything is it's all in a scene graph, it's not something we have to worry about. But we still have sort of the same thing when we talk about the hierarchy. So at the moment, if I move my box side to side, it doesn't affect the sphere. But if I make the sphere a child of the box, it's effectively, if I say move the box a certain amount, it also moves the sphere by that same amount. So it's the same sort of thing. Putting things, I guess the main difference between having a scene graph and having like regular things or regular GL, or regular graphics, sorry, is like if your scene graph looked like this. So every single item was a child of every item before it, such that moving any one thing would move them all accordingly. Does that make sense? Hopefully. It'll take a little while to sink in, I'm sure. But let's take a quick break there, and then we'll come back and we'll look at some more examples of transformations. All right, so let's get back into it. So I've got translate x, y, and translate x, y, z here. So this example only deals in x and y, but obviously x, y, z is the same thing. It just means that in addition to moving x, so side to side, and y up and down, we can actually move things closer or further away from the screen. And as you would expect, as they move further away from the screen, they get smaller, just like how if I held this in front of your face, it would look a lot bigger than if I held it back here. So that's just moving in the z-axis. Okay, the next one is scale, and we have a nice example of that, which is super counterintuitive to start with. Let's get rid of that. Scale. So this is scale. So it looks to us like, at the very least, these things are getting larger and smaller, but they are also, the white one's also moving from one side to the other. If you really want to get complicated, it looks kind of like this, where they're both moving away, and as they are moving away, the green one is swinging around the other one. But it's actually not. So this is solely done with scaling operations. So if we have a look in here, just to not surprise you guys, there's a scale, and there's a scale, and well, there's a translate, I suppose, but that's at a fixed value, and that's at a fixed value as well. So really the only thing which ever changes, the only thing which has a variable, is the scale value here. So what's happening here? So to go a little bit deeper into graphics, what the translate and scale and rotate values effectively do is they get multiplied by each vertex you're going to draw. So if I'm drawing a square, and this is x equals 1, y equals 1, x equals 2, y equals 2, 2, x equals 2, y equals 1, whoops, x equals 1, y equals 1. So this is a cube. X equals 1, y equals 2, x equals 2, y equals 2, x equals 2, y equals 1, x equals 1, y equals 1. Everyone happy with that? Makes sense? So if I did something like translate 10 by 5, like that, effectively what that translate function is doing is saying add 10 to the x value of everything and add 5 to the y value of everything. So it's actually doing, this is basically the math which happens at a lower level. So you just say translate and draw that. But what the your graphics card will do is it will actually add all of those translation values to all of these. So this suddenly becomes x equals 11, y equals 7. Let's leave that one there and I'll do it in a different color. So what ends up happening is we say, okay, x equals, well, let's do the points. X equals 11, y equals 7. Then this one becomes x equals 12, y equals 7. Then we have x equals 12, y equals 6. And x equals 11, y equals 6. And if we draw all those things up, it looks like that. And effectively, what we end up seeing is that this cube has moved 10 units in that direction and 5 units in that direction. So by changing each of these vertex values, by adding these to them, what we've effectively done is done this translate by 10 in the x dimension and 5 in the y dimension. That makes sense? Everyone happy with that? So the reason why that is important is because if translate is adding, then scale is multiplying. So let's say I have scale 2. One, two, 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 one, one, one. This is the same box we had before. So what a scale does is it multiplies each of the values by the scale value we give it. So scale 2, or depending on which language you have, might be somewhat more like scale 2 by 2 by 2. And they don't all have to be the same. As we saw in Unity, we can scale something really long in one dimension and not so long in the other to stretch it out. But if we do scale, we're only working in 2 dimensions at the moment. Let's do scale 2 by 2. As I said, if translation is adding, scale is multiplying. So if we go through and multiply all these things again, 1 by 2 is by 2 by 2 is going to be 2 by 4. 2 by 2 is going to be 4 by 4. 2 by 1 is going to be 4 by 2. And 1 by 1 is going to be 2 by 2. And if I draw all these up, I didn't do a very good job of drawing this, but theoretically this should be twice the width and twice the height. But because this starts at 1 by 1, this is also now twice the distance. So if this is 1 pixel here, or 1 unit here, that's 2 units there. And likewise, what was 1 unit here is now 2 units there. So it has doubled the size, but it's doubled the size relative to the origin effectively. So it's doubled it, but it appears to have actually also moved it. So what we're seeing in this example is we have 2 squares. Actually, no, let's do one more example before we do that. So let's draw our original square again. 1, 2, 2, 2, 2, 1, 1, 1. And let's say instead of doing 2 by 2, let's do -1 by -1. So it's multiplication, right? So -1 by -1 by 1 by 2 is going to give us the value of so what's 1 times -1? Yeah, and what's 2 times -1? Cool. So our first one is going to be -1 by -2. 2 by 2 is going to be 2 by 2 scaled. So it's going to be -2 by -2. So we're just literally multiplying each of them by -1. 1 by 1 is going to be -1 by -1. And 2 by 1 is going to be -2 by -1. So our box, if we multiply it by -1, it's going to be the same size, but it's actually flipped. In this case, it's because it's -1 by -1, it's flipped both across the x and then across the y. So if we drew a label on this to indicate its direction, so that's the top left corner, and this one, that arrow would point that way. So it's flipped. If the scale value is below 0, it's a mirror image effectively. So imagine we had a mirror here and a mirror there. What we would see in that corner would be a -1 by -1. Okay, so what's actually happening in this example? Well, everything's being scaled by the value of s, which if we print this out, we will notice goes from about -2 to about 2. So we have two boxes which are drawn here. One is in the center of the image, and basically that's going out this way, and then so it goes up to 2, and then it goes down to 0, and then it goes out to -2. So that's actually going like this effectively. And actually we can show that a bit clearer by if we take that, oh no, because I've done a rect. I was going to say if we drew, actually we might be able to. Let me see if I can quickly do this. Open, no. File, examples. Where was that RGB Cube? Topics geometry. So if we take one of these quads and replace our rect by it, so we want that to be 0, 0, 50, 50. Oops. And where did my RGB Cube go? Grab that color mode. All right, hopefully this will work. Okay, so it didn't, which is a shame. I think it's way too big by the looks of it. Okay, so that didn't work, which is unfortunate. But what I was trying to do is get it to draw, rather than just a solid color, have it to have all the colors a different corner, because what we would see is because we're scaling it by this corner, so this corner here, the top right corner, when it goes the other side is now the bottom left corner. So they're flipping just like this one here is flipping, but it's because it's in the middle, it's flipping diagonally on top of itself. This other one here is actually sitting out here. So as it gets closer to 0, all those numbers get closer and closer to 0. And then as it goes into the negative, it gets bigger and bigger out on the other side. So what's actually happening is it's going from side to side like that, each of those numbers, because they're getting multiplied out. And that is making it appear like it's actually swinging around the other one, when in reality all it's doing, if we just take one point, for example, at 3, so let's say that's the center of this white box, as we scale towards 0, so it'll go 3, and then it'll go 2.5, and then it will go 2, and then 1.5, 1, blah, blah, blah. And when scale finally equals 0, that will be at 0. And then as it starts to go into the negative, so if scale equals -0.5, that's half of 3 will be negative 1.5, and then as scale eventually reaches negative 1, eventually that will be out at negative 3. So it appears like it's shifting from side to side, but really it's just scaling around that, that origin point of 0, 0. So that's it's a little bit confusing, but it's just important to know that scaling doesn't, in the real world, we're used to things shrinking from, well, you can make something bigger, which is a scale of greater than 1. You can make something smaller, which is a scale of less than 1. And eventually you get to 0, where you've made something so small it's collapsed into nothingness. But in 3D geometry, because we're just dealing with maths, you can actually scale into the negatives, which is a flip. And so I have an example talking about that. But the same thing is true of in Unity. So if I grab something, actually no, let's grab, where's that whale gone? So here's my whale here. And if I shrink him, so I use the shrinking tool, so he's facing towards our right. If I grab that one and shrink him, you notice it's getting smaller and smaller, so you can see in the scale his Z value is getting smaller. So it started at 1, and it gets smaller and smaller and smaller until we eventually reach 0, where he's collapsed on top of himself, almost. And then as we start going into the negatives, you'll notice it's facing the other way now. So in fact, when we get to negative 1, it's now a complete mirror image of where we started from. So if we flip between the two of them, we can see that that has scaled it. And likewise, if I put in, let's grab one of our little characters. So let's put that bat out there. He's already quite small. Needs to be bigger than that. Okay, there we go. So if we take our bat here, let's just rotate him. Oops, so he's facing the camera. Let's get rid of that. Oops. Where's my bat? Sorry, just bear with me for a second. Okay. So now we have our bat and our killer whale. So if I take that killer whale and make it a child of the bat, because remember I said before in our 3D graphics, it's like if we had all our geometry as children of each other. So the killer whale is now a child of the bat. So if I move the bat, the killer whale will move. If I now scale the killer bat, we'll notice that the killer whale is shrinking, but it's also moving closer and closer to the bat, just like that box appeared to be doing. And eventually, when we get down to 0, the killer whale will be almost entirely on the bat. And then as we go into the negative values, he's going to appear on the opposite side, mirrored. So this is exactly what we saw in that other demo. It was just looked kind of like this. So it was going. So it looks like, the killer whale is kind of moving around, rotating around the bat, but really we're actually just scaling them and resizing them so that they appear as a mirror image of themselves. And you can see the only thing I'm doing is changing that X scale value, and that's causing the whole thing. So that's the exact thing we had before with our scale example. And the last transformation that we're likely to see is rotation. So we know what scale and transform does, and all rotation does is spin things around an axis. So like we said before, to translate an X, we'll move it to left and right. To rotate around X, we'll rotate around that axis. So if X goes this way, rotating around X will rotate around that way. Likewise, if Y is up and down that direction, rotating around Y is like rotating around that axis. And if Z is that way, then rotating in Z will rotate around that. And so this is just an example which draws two two rectangles and rotates around them. The only thing here to consider is like we talked about our example with the pointer of, if I move this by 10 and then 5 and then draw something, and then move by 10 and 5 and draw something, they'll be relative to each other. The same thing happens with rotations, and rotations where it gets a bit tricky. So if I move this out to here, or if I start from here, moving in the x dimension, so if I say translate x 10, will move me 10 units that way, right? But if I rotate this 30 degrees that way, moving 10 units in the x dimension actually moves me on that diagonal, because we're talking about relative to this card. So if the x dimension is pointing that way, moving 10 units will move me in the direction of the pen. But if I rotate first and then move, I'm still moving in the direction of the pen. So I'm still moving up that way, even though for me, I feel like if I move 10 units in x, I should actually move over that way. So I'll show you again an example in Unity. Okay, so this killer whale is, let's put everything back to normal. Okay, so this killer whale is negative 0.5 units. Actually, let's flip the camera around the other way and let's do it this way. Where's he going? Okay, so this killer whale is 0.5 units away from my bat, right? So if I rotate my bat like that, we can see the killer whale is rotating as well. But the killer whale is actually still 0.5 units away. So if I move it by 0.1, 0.2, you can see moving in the x dimension is moving him in the relative to the bat's x dimension. So you can see the bat's x dimension here. If I go back and set that bat to where it was before, as I rotate it, using that one there, as I rotate it, we can see the bat's x dimension changes its orientation as well. So 5, when I say move the killer whale 0.5 units to the x of the bat, it actually depends on which way the bat is facing as well. So if the bat is rotated 90 degrees, for example, what was previously my x now has the same effect as moving it in the y. Does that make sense? So it's kind of complicated stuff, but unfortunately that's the way it works. And the good thing about things like Unity and stuff, and why we decided to make the assignment in Unity this year, is because it's much easier to figure out why stuff isn't going. If I wanted to say, rotate the bat by 90 degrees but still have the killer whale where he was before, I can just say, let's make him not a child, rotate the bat 90 degrees, and now he's 0.5 units from that position. Whereas if you were to do the same thing in OpenGL, you'd need to use, or in processing, which uses OpenGL, you'd have to use this push matrix and pop matrix to save, do the rotation, or save it, do the rotation, draw the bat, pop it to load the old position, and then move it around.
There is any way to make the axis rotate in relation to the wall instead of the object?
Yes, so there actually is. So the question we just had is, can we rotate, well, I'm paraphrasing, so if I'm wrong, we want to be able to rotate the bat, but still move the killer whale, which is a child of it, in relation to the real world. Yep, so we can actually do that in Unity. So if let's just move this killer whale to be on top of the bat, so when I rotate him, it doesn't move away. So if I move this by 0.5, he appears there. Okay, cool, that's where I want him to be, but I also want to rotate the bat first. So I want to rotate the bat by 50 units. So if I tried to move this I move the killer whale now, it's moving along that axis. But what I can actually do is we'll see up here this little thing which says local. And if I move onto it, that's a very confusing tooltip. But what local does is it basically means move it in the local space. So move it relative to its place in the hierarchy. So if the bat's been rotated 30 degrees and its x-axis points in this direction, all of my tools will also point in that direction. So what I can do is I can click on that, and that will move it into global, which is in world space. So you'll notice now that it doesn't actually point in the direction that the whale is facing, it just points in X and Y, and I can shift that whale out in that position. What we'll notice though, is as I'm moving this, so before, if I move this in local, if you see the position, only the X value of the position's moving. But if I change this to global and then shift it, you see both the X and the Y values are moving because it's moving it now in the world space. So in order for me to shift this out here, I need to move in the X. So if I did just this, you'll notice he's still moving in that diagonal. So I need to move him now down a little bit to end up in the same relative position. So that is something which is really easy to do in Unity. You just have to click one button. To do this, to do the same thing in processing is a lot harder. So we will come back to an example of that a little bit later on. Okay, so now let's go into some more detail about these things. Anyone here a mathematician or really into maths? I can tell by the looks on the looks of disgust on your face that no. So basically, these are just what's happening behind the scenes for these various things, and we've actually already talked about them and we've done examples of them. So this is just sort of covering it. So 3D translation, we're translating some object by an X value, a Y value, and a Z value. So we're moving it in space. In processing, the command is translate the amount we want to move in X by the amount we want to move in Y by the amount we want to move in Z. And so if you think about before we were doing this with translation and we said translate 10 by 5 means we add 10 to the value of every vertex as X and we move 5 to the value of every vertex as Y. Everyone remember that? Yep. So we talked about how translate is adding. So translate 10 by 5 would mean we add 10 to this and 5 to that and 10 to this and 5 to that and 10 to this and 5 to that and 10 to this and 5 to that. So it's adding. And you can see here are the actual formulas for doing so. So if we have our original X position, we add the value of Tx to get our new X position. If we have our original Y position, we add the value of Ty to get our Y position. If we have our original Z position, we add the value of Tz to get our Z position. So this is basically the linear equations for doing this. The way things are actually usually represented in 3D graphics is with this matrix here, which is known as the transformation matrix. And anyone here ever done much matrix multiplication or anything? Yeah. Yep, one person, two people. So basically, this is a way of representing these equations here. So we have this is our original position, our original X, Y, and Z. So these are our original vertex positions. And then if we multiply each of these out by this matrix, I can never get this right the first time around, but I'm pretty sure we go multiply that by that, that by that, that by that, that by that, and add all four of them together to get X. Then we multiply that by that, that by that, that by that, that by that, add all of them together to get Y. That by that, that by that, that by that, that by that, add them all together to get Z, and So the only one I'm going to do off the top of my head is, actually no, for translation we can do them all. So if we go multiply all of these by all of these, we're going to get 1 times X, X, plus 0 times Y is 0, plus 0 times Z, 0, plus Tx times 1. So if we shrink that down, we get X plus Tx, X plus Tx. Do the second one, 0 times X is 0, plus 1 times Y is Y, plus 0 times Z is 0, plus Ty times 1 is ty, which simplifies down to y plus ty, which is our second one. Third one, 0 times x, 0 times y, oops, 1 times z, and tz times 1 simplifies down to z plus tz, which gives us z times z plus tz. And our final one, 0 times x plus 0 times y plus 0 times z plus 1 times 1 equals 1, which gives us this last one in here. So that's a very simple version of, this was probably more for me than it was for you to make sure that I can still remember how to do this stuff. But this is basically how we get these equations from here. This, you might be asking, what's this 1 here and this row here? So that in three-dimensional geometry, we can have two types of, I don't even know how best to describe a thing, let's say. So you can have a point or you can have a vector. So a point is something which is discrete. So there is a point right there. A vector is a direction which passes through that point effectively. By having the value 1 there, we're saying it's a point. If that was a value of 0, it would be a vector which passes through that point. And these are vectors which don't actually necessarily have a start or an end. So I've ended my line here, but in reality that goes on infinitely, and this goes on infinitely. The only thing we know about this thing is its direction, and then it passes through this point. Don't worry about what that means. Just that's why it's 1. If it's 1, it's a discrete point. If it's 0, it's a vector. But all you need to know is that that last number, when we're multiplying these things out, x, y, z, and you have the 1 at the end, and then everything will multiply out nice and neatly. Okay, so that was a pretty simple example. I said translation is addition. You know, these things show it. We worked our way through the matrix and we showed it. Nice and easy. Scaling, I mentioned is multiplication. So we multiply 1 by -1, 2 by -1, 2 by -1, 2 by -1, 2 by -1, 1 by -1, 1 by -1, 1 by -1. We multiply each of the values out by the scale. So for scaling, we basically need to let the computer know the scale factors x, y, and z. So in this case, they were the same, but it could have been 1. If we'd have done -1 by 1 like that, we actually would have ended up, where's my green pen? If we'd have scaled this original marker here by -1 by 1, does anyone want to hazard a guess where the box would be? If we say this is quadrant 1, 2, 3, and 4, where is it going to be? 1. Yep, so multiplying by -1 means the x values are going to be negative, and multiplying by 1 means that the y values are going to be the same. So this, if we multiplied by -1 by 1, what we'd actually end up with is our box looking like that. Does that make sense to everyone? So we're just multiplying that x value by -1. So 1 becomes -1, 2 becomes -2, and so on and so forth. So yeah, those numbers, we had them the same before, but they don't have to be the same. To use this in processing, scale x, scale y, scale z. As I mentioned, scaling is multiplication. So if we have our original x, y, and z position for a point, we multiply that by the scale x, scale y, and scale z positions to figure out our new x, y, and z positions for that point. And this is the matrix for that point. So if you remembered in our last one, we had 1, 1, 1 there. Now we have scale x, scale y, scale z there, because this x will multiply by x. Oh, sorry, this sx will multiply by x, this sy will multiply by y, and this sz will multiply by z to give us these formulas again. Not that complicated. There are different types of, sorry, I got my braces tightened yesterday, I just bit down on them. So we have different types of scaling. So a scaling of greater than 1 means we're enlarging something, we're stretching it. So if we have our killer whale here, oops, and I increase his Z scale, he will get bigger and bigger and bigger. So that is increasing it beyond the value of 1. Scale value of 1 is its normal scale. A scale value between -1 and 0 will shrink it. So if I shrink that scale value down, it will get smaller and smaller and smaller. Once we hit 0, we've decimated it. Essentially, we've completely flattened it. So if I get my whale here and set his Z value to his scale value to 0, it looks kind of weird because of the lighting, but my whale, you can't actually see him from the side anymore because he's effectively infinitely thin. If we have less than 0 but greater than or equal to -1, we're shrinking and reflecting it. So if we go below that value now, oops, whoa, there we go. So if we go down to 0 and then we start going into the opposite direction, he's shrunk, but he's facing the opposite direction. When we get to -1, again, he will be normal size. Sorry, those are all relative to the... It will be normal size, but facing the opposite direction. And if we go greater than -1, it will be stretched and in the opposite direction. So those are the different types of scaling. It's what we're used to in the real world is pretty much just those things there. Like if you think about like a balloon, if I stretch it, I can stretch it out, I leave it to its normal thing, and then I can sort of push it together to shrink it. And if I was super strong, I could push it so much that the atoms just disintegrate and we decimate it. But unlike that, we can actually pull it into a mirror image universe in 3D graphics. There's nothing preventing us from doing that. So here are some reflections. So if we want to flip around a certain plane, so if this is X and Y and Z out towards us, rotating around a plane which is formed by the X and the Z, so this plane here, kind of like the desktop, what we would do is we would multiply by -1 in the y-axis. So multiplying by -1 will flip it across the y-axis. If we want to multiply by the y-z axis, we multiply by -1 in the x-axis and so on and so forth. And this is what the mirror thing looks like. So this is flipping in the x-axis, so doing this operation, we have a -1 there. So x will equal -x. Okay. Rotation is where things start getting tricky from the math. And I'm not going to go through this in too much detail or expect you guys to know how this works. But basically, when we rotate around... Sorry, I cut myself washing dishes last night. I'm falling to pieces at the moment. I just made myself bleed again. So rotating around x-axis, the x-axis is if we think that the x-axis is moving side to side, rotating around the x-axis is putting our hand in that direction and rotating it that way. So if we're rotating around the x-axis, we're rotating that object in that direction. In processing, to rotate around the x-axis is just rotate x, and theta is the angle you want to rotate around. This is where things start getting a little bit complicated, because depending on which axis you're rotating around, the rules and the linear equations and the matrix equations are different. So rotating around the x, geez, that's really, grab a tissue. So if we rotate around the x-axis, if we think about the x values of all these points, so this is the x value, this is say 1, 2, and 3. This will actually still be 1, this will actually still be 2, and this will actually still be 3, but the y values and the z values will have changed. So likewise, our x value gets copied straight across, so we have this 1 here, and for our y and z values, they're a combination of sines and cosines and negative signs around those x and y things. I'm not going to go into any detail because I'm just likely to confuse myself if I do that, but I have been working with this stuff for like probably over a decade now, and I still have to look this up every single time I need to do it. So do not, there's no expectation that you guys will memorize these formulas for rotation around various axes. So that's x-axis. If we have a look at y, so if we compare these two, cosine, negative sine, sine, cosine, cosine, sine, negative sine, cosine. So not only have they moved, so now that it's not just the y and z, it's the x and z, but also those signs have flipped. And this is what confuses the hell out of me because I can never remember which way, like, you know. So here we have negative sine and sine, so negative is in the bottom left, and here negative's in the top right. So yeah, I have not really taken the time to think about why that is that they flip over, but that's what happens. But again, rotating around the y-axis, if y is floor to ceiling, we put our hand joining one to the other and rotate around our arm. So it's rotating around that way. Likewise with x, rotating around y doesn't actually change our y values, so the y value here and the y value here of those points will all be the same, but the x and z values will change. And with z, so z has the similar thing to x in that we have sine, positive sign in the bottom left and negative sign in the top right. So positive left and negative left. They only swap on the y, and I can't be bothered trying to figure out why. So there we go. Those are the equations for rotating around the z-axis, which again, if it's front to back, point your arm that way and rotate, that's the way the object will rotate. And likewise, as rotation around x in processing is rotate x theta, rotation around y is rotate y theta, rotation around z is rotate z theta. Okay, let's see if we can get through. We've got a couple more. Let's see if we can get through at least this slide before we break. Okay, so if I wanted to rotate around a pivot point, so we saw this example in processing, in Unity, sorry. Let's reset everything's positions, rotations, and scales. Okay, let's make my bat a bit bigger. So we can see him. Okay, so here's my bat and here's my whale. Now, as I said, in 3D geometry, in non-scene graph stuff, everything acts as if it's a child of the previously drawn things. So we'll make our killer whale a child of our bat. So if I rotate around the origin, we'll notice that the killer whale is rotating around the point of the bat. So it's not rotating, if we think about it, it's not rotating around the killer whale, it's rotating around some arbitrary point, and as that turns, it spins around as if it's attached, as if there's like a pole attached out here connecting the two of them together. But what if I did actually want to rotate the killer whale around some point on its body? Well, basically what we have to do is we have to figure out the point of the body we want to rotate it around. So let's say we want to rotate it around this point just at the base of its tail. And I actually have to shift my killer whale so that that point, assuming that the bat is the origin, move that point so that that point is now at the origin. And now when I rotate my whale, it will rotate around that point. So it's rotating at the base of the tail. So what I can do is if my killer whale is out here and I wanted to rotate it, I can shift it in. So the point I want to rotate it around is there. Then I can, rotate around that point. And then when I'm done, I can shift back to where we started from. So that's effectively, if we thought about those two things, what that would look like is that the whale has stood up on its tail. And that's exactly what we have to do if we want to rotate an object around a point in 3D geometry. So say we've got this triangle here which is sitting out some distance from the origin. if I rotated, what would happen is it would actually spin around that entire origin at that distance from it. So it would go like that. But if I actually just wanted to spin it on the spot, like we see in this example here, what I'd have to do is I'd have to move it so that that point was at the origin, so that the triangle was like that, do my rotate, and then shift it back by the same amount. Does that make sense? Hopefully. So the transformation sequence for doing that is we translate, so if the point we want to rotate around is xp, we wrote xp, yp, zp, we translate by negative xp, negative yp, negative zp, which in this case will shift this triangle down like that. Then we do our rotation, so rotate z around theta, which will rotate that way, and then we're going to translate by xp, yp, zp again, which is just going to shift that back to where it came from. So instead of this whole thing rotating now around that point, we've shifted the point, rotated it, and then shifted it back again. This transformation sequence, again, same thing. Translate by negative xp, negative yp, negative zp, rotate around theta, and then translate by xp, yp, zp to put it back where it was again. And if we draw this out, or write this out, this is the matrix math for it. So take our original points, translate by negative xp, negative yp, negative zp, do our rotation around z, and then translate by xp, yp, zp. And the good thing about matrix math is we can actually multiply these things ahead of time. So we could multiply this by this, and then the result of that by that, and that will condense the whole thing down into one transformation matrix, which we can then multiply about. So we can actually, rather than having to do this, multiply by this, the result of that multiply by this, the result of that multiply by that for every single point, we can just multiply these three things together to get one matrix and then do all our processing. And in fact, when we talk about, we have our coordinate, our world coordinate, and we've moved it some amount, we've rotated it some amount, we've scaled it some amount. The position and orientation and scale of that is represented in that form. So you have what's known as the model view matrix in computer graphics, which is basically this cursor, where it is, what direction it's facing, how big it's been scaled or whatever. So matrices like this are basically inseparable from 3D geometry. Okay, let's stop there for today because I think that's enough. I'm boring myself, let alone you guys. So we'll have a little break there. As I said, if anyone wants to have a crack with any of the examples we looked at, trying to change the color, take that cylinder example and try and make it so it has a nice color around it, be my guest. Again, it's not a required homework assignment or anything, but if you want to learn something, doing is the best way to get good at it. What was I going to say? We will try and get you the assignment. I'll probably be aiming to give it to you guys next Thursday. And you'll have about 3 or 4 weeks to get it done. And hopefully by next Thursday, because again, I don't want to give you an assignment on stuff I haven't taught you. So hopefully by next Thursday, we'll be at the point that you guys will be ready to make a start on that. Cool. Any questions, concerns, comments, queries? All right, cool. Cheers, guys.